Hello and welcome to this tutorial on an introduction into the induction machine. What I'm going to go over today is a very brief overview on the construction of an induction machine and how some of those things will influence the characteristics of the induction machine and how it's used, and how it's used often has no bearing on some of its characteristics. So the induction machine is most commonly associated with what's called the squirrel cage, and it's probably a good way of understanding how they're built. They don't have to be built with a squirrel cage. They can have what's called a wound rotor, which is like the normal rotor out of a lot of machines with windings on it, and all you do is you short them all together, and that creates what's basically a glorified big hunk of metal, which is pretty much what the squirrel cage is. So the squirrel cage it's called a squirrel cage because it looks like the sort of cages that squirrels or hamsters would use if you capture them and put them in a thing. And it's essentially like this, with a series of bars, and they're actually called that, along like this. And it's built, usually these are made out of aluminium, and they are often have got a series of laminations in there as well when you see the pictures. But what I'm doing here is a descriptive a picture, and that shows you basic thing. Obviously there needs to be some way of mounting these, and you know there'll be something through here connecting these 2 points together, and then there'll be a shaft coming out here which is on some bearings, and same on the other side as well. A way of doing this with a shaft on some bearings. So the whole thing is going to rotate in this direction. Now, that squirrel cage is put inside a series of magnetic fields, and an induction machine to work needs a moving magnetic field. If that magnetic field is not moving, the machine won't work. And indeed, this is one of the reasons why a lot of the early opponents of the induction machine said it would never work. And in reality, it obviously does, because they've been around for 100 years. So with this sort of rotor, we then have a series of poles that go around it, which we might draw like this. There's our pole there, and it's going to have some windings around it, and we'll have one on the other side. Like this, and that'll have our windings around it. But that's not enough. We need multiple phases to get that moving flux field. So these are almost always used in three-phase. There are some where they get used in single phase, but what they do is they effectively do a cheat, and they will use a capacitor to give a phase shift to a second set of windings. So you might have a second set of windings where my fingers are here, with a capacitor connected off to your single phase that will do that. But for the purposes of this, and indeed most induction machines, we're going to look at it with three-phase. So we need to draw another set of poles over here with their windings and its mate over this side here. And then the third one, which we'll draw here, with its windings, and its mate will be sitting up here on this side here, like that. And these would typically be labelled as being phase A, and then phases A mate, often called A dash, phase B, and it's normally done clockwise but not always, phase C, and then this one over here would be B dash, and this one here would be C dash. So we've got our three phases. Each phase is, from a load point of view, is split into two windings. And this is what's a typical thing. Now, this is where some of the language gets confusing, and that is around what is a pole. Now, some textbooks, some websites, some videos, some lecturers, some of your tutors use a lot of these words interchangeably. So technically, that is a pole, as is that. They're both poles. However, one pole by itself is worthless. So what we often talk about is we'll talk about pole pairs. And that would be, in case say A and A dash, or maybe B and B dash. That is a pole pair. So this machine that I've drawn here has 6 poles, and you could argue it has 3 pole pairs. It has this one, and this one, A, B and C. However, a lot of the language would ignore these auxiliary poles because they are basically 120 degrees extension of these ones. So this machine here would often be called a 2-pole machine. Okay, even though technically it's got 3 pole pairs and it's got 6 poles, it's still called a 2-pole machine. And this is the sort of thing that confuses a lot of students initially when they do their calculations. One of the reasons it messes a lot of students up is because one of the basic equations for an induction machine is that the synchronous speed is 120 times the supply speed over the number of pole pairs. And if you get this number wrong because you plug the wrong one in, this number will be wrong and all the rest of your calculations will be wrong. And we'll be going through some of that in a minute. Now, the other thing is, because each of these phases has got 2 windings, we could draw it over here as being like this, and that could be phase A, and that would be A dash, forget that, and this would be phase B, and this would be B dash, and this would be C, and this would be C dash. We can configure that, we could configure that in, we could configure it in star, 3-wire star configuration, that would work. Or we could configure it in a delta configuration. That would work as well. So either of these would work, and it doesn't really matter, as we'll come through in a few minutes. Now, one of the other things we need to understand and look at and just keep in the back of our mind when we're looking at induction machines is the torque speed characteristic of them. And the torque speed characteristic of an induction machine typically looks a little bit like this, where this is torque on the y-axis and this is speed on the x-axis. Now there are several really important points in here. This point here is a really important one, because this is our maximum theoretical speed. This is NS. Okay, this is the maximum speed that we're going to get. And it's worth noting that at normal rate, what we would call rated speed, or what's actually called the synchronous speed, is the proper term for this. At this speed here, there is no torque in the machine. And the reason there's no torque in the machine is because at this speed here, this rotor is moving around at the same speed as this magnetic field is moving around. So therefore the lines of flux and everything like that are not going to be doing any work. So I'll probably, at this point here, it's probably time to take a little nip back and look at how this works. This sets up a magnetic field. It's a moving magnetic field. And you know that if you have a conductor in a moving magnetic field, a current gets induced in it. So what happens is currents get induced in this here, in these bars. And each of these currents has got its own magnetic field, as per the right-hand rule, current, field. What happens is this magnetic field interacts with the magnetic field out of the stator, and that is what does your movement. As per the, you remember all of this sort of carry on. Now, coming back to here, we can see that the machine will have maximum torque at this point here. Okay. That point there is called the breakdown point. It's also called the pull-out. And at that point there, the machine is operating at this speed here at maximum torque. reality is we tend to operate the machines down here somewhere. This is at 100%. And you can see here that both of these points are less than the synchronous speed up here. So this difference, the difference between the speed of this rotor going around the outside, the electrical speed, the synchronous speed, and the rotor speed is called slip. And slip is, as I said, the difference in speed. And we've got a rotational speed through here, through our magnetic field. We've got a rotating speed of our rotor, which is on the shaft. That's actually the one we're really kind of interested in. And the difference between is called slip. And the expression, it's simply a ratio. Slip is the synchronous speed minus the rotational speed of the rotor over the synchronous speed. And it's usually expressed as in a percentage. So, if we want to go through a few numbers here on a machine, we'll say that the nameplate of the machine that we're going to look at let's say it's a 5 kilowatt machine, and it's operating at 50 hertz is what it says, and it's got a line voltage of 400 volts, and the slip is 5%. And the other thing is it's a 4-pole machine. So from what I was talking about before, we say it's a 4-pole machine. It would actually mean that there are 12 actual poles here. Okay, it'd be basically these 6, which is a 2-pole machine, doubled. So there'd be another pole placed in between each of these. There'd be one here, there'd be one here, there'd be another one here, 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 and here. And we would have 2 lots of these, 2 lots of A windings. It would go A, B, C, A dash, B dash, C dash, A, B, C, A dash, B dash, C dash, as it works its way around. Right, so using these numbers here, we can pretty easily and quickly find out that what we call the synchronous speed of the machine, the speed here, the speed of the field moving around the outside, as I said up here, NS is 120 times the frequency over the poles, which is 120. This is a 50 hertz machine, and there are 4 poles in it, and we do that, and that will give us 1500 RPM. It says the machine has got a slip of 5%, so from that we can find out the rotational speed of the machine. We can rearrange that equation, and that will give us that, which means 1 minus 0.05 times 1500 equals 1425 RPM, which is the same as 148.5 radians per second. So our machine, which is rated 50 hertz, 400 volts, 5 kilowatts, at rated load, the shaft of this machine, this 5% point here, this point here, will be moving at 1425 RPM, or 148 radians per second. The question is, what will the torque be? Well, we can find out torque fairly simply, because we know that mechanical power is rotational speed times torque. We know that it's a 5 kilowatt machine. We know the torque, so we can find out the speed. We know the speed, sorry. We can find out the torque. So torque is power over speed. 5,000 over 148.5 gives us 33.6 Newton meters. So based on the nameplate, we can understand a lot of how this machine is going to work, what its rated speed will be, how much torque it'll be delivering, and how that works. The big thing that people often have issues with induction machines is this notion around slip. We'll probably come back and talk more about that, but this is enough for now. Thank you for watching. Have a good day.